Welcome to our lesson on liquid pressure. First off, I want to state that calculating liquid pressure can be calculated the same way as you calculate pressure by solids. However, we will be learning a new and different way. What is that way? Well, let's see. Let's proceed by deriving the formula for calculating pressure exerted by liquids. We'll start off by looking at our first formula we learned for solid pressure. Recall that pressure is equal to force divided by area. What force does an object exert? Well, in this case, we are looking at the weight of the object. Recall that weight is equal to mass times gravity. Also recall that mass depends on volume and density. In particular, you should know that mass is equal to density times volume. If we were to substitute those into our formula, P equals F over A, then we'll get that the pressure is equal to mass times volume times gravity divided by area. But recall that volume is equal to length times width times height, and area is equal to length times width. So if we substitute those into our formula, we will get that the length times width cancel out. So we have that pressure is equal to density times height times gravity. If we rearrange that and put it in alphabetical order, then we get our formula. Pressure is equal to rho GH, where rho is just the Greek symbol for density. Looking at our formula, let's analyze how these factors affect the pressure of a fluid. Well, if we look at it, we see that we're multiplying density times gravity times height. Since we're multiplying all three of those, then all three of them are in a direct relationship. Meaning that if we were to increase any single one of those, we would increase the pressure. So that means that salt water exerts a greater pressure than fresh water, because salt water is more dense than fresh water. Gravity, if you were to increase the gravity, then you would increase the pressure. Let's say you had a container of water here on Earth, and you then took it over to Mars, where there is increased gravity. Then the pressure in that liquid would increase as well. And finally, the height. The height or the depth, whichever way you want to look at it, if you're above, you would say how deep the water is. If you're at the bottom, what height of water is above you. The deeper the water is, then the greater the pressure. However, under normal circumstances, we will say that the pressure of a liquid only depends on two of those factors, namely the density and the depth, aka height. We would normally say that gravity doesn't count because under normal circumstances here at the Earth's surface, gravity is a constant. Only if you were an astronaut traveling to other celestial bodies, then would it make a difference. One thing to note that does not affect the pressure of a liquid is the shape of its container. As we see here, the liquid, no matter what the shape of its container, will find its own level, as we say, water level, right? And so the shape of the container does not affect the pressure. The only thing that would affect the pressure in these instances here, since it's all the same liquid, is how much water is directly above it. In other words, depth, aka height. Now, let's do an example where we calculate some liquid pressure. What would the increased pressure be at the bottom of a pool that is 2 meters deep? Well, let's assume that it is filled all the way up with water, which has a density of 1,000 kilograms per cubic meter. Gravity, we'll assume, is 10 newtons per kilogram here on the Earth's surface. So substituting into our formula, P equals rho GH, we will have that the pressure is equal to 1,000 kilograms per cubic meter multiplied by 10 newtons per kilogram multiplied by 2 meters. So that will give us an answer of 20,000 pascals or 20,000 newtons per square meter. Easy, right? Now we come to Pascal's principle, which has many everyday applications, as you'll see shortly. Pascal principle states that a pressure change at any point in a confined incompressible fluid is transmitted throughout the fluid such that the same change takes place everywhere. So what exactly does Pascal's principle mean? Well, you can think about playing with a little plastic container that has liquid in it. If you squeeze one end, what happens to the liquid? It rushes to the other end, right? That's because there are some air pockets in it. But imagine if it was exactly filled with water and there were no air pockets in it. If you were to squeeze one end, would it rush to the other end like that? No, because it's incompressible. There is no air to be squeezed. Alright, so the pressure that you apply at one end, at that point, is the same pressure that will be experienced all throughout the other parts of that confined liquid. So let's look at an example where we can use Pascal's principle. Hydraulic jacks, those kinds that are used to raise heavy vehicles, those use Pascal's principle. Even the braking system in cars, those use Pascal's principle. Let's take a look at an example then. Let's say we have this hydraulic jack system. We have a 25 kilogram mass that is over a piston of area 250 square centimeters. On the other side, we don't know what force is needed to balance that system, but we do know the other piston has an area of 10 square centimeters. Using Pascal's principles formula, which is F1 over A1 equals F2 over A2, then we substitute those values. What do F1 and A1 and F2 and A2 stand for? Well, they're just corresponding force and area values for these two pistons. They are equal to each other since, according to Pascal's principle, the pressure is the same everywhere. So the pressure on one piston, which is its force divided by its area, is equal to the pressure on the other piston, which is its force divided by its area. So substituting our values, we have 25 over 250 is equal to our unknown weight over 10. Here, it is not necessary to convert those square centimeters to square meters. The reason is because in the very next step, they will cancel out. To find the unknown mass, we take the 25 kilograms multiplied by the 10 square centimeters and then divide it by 250 square centimeters. In that step, the square centimeters cancel out. That's why it's not necessary to convert them to square meters. And so we're left with 25 kilograms times 10 divided by 250, which gives us 1 kilogram. So it is only necessary to have 1 kilogram to balance that 25 kilograms. That's the same reason why just a little tap of your foot can bring this big massive car to a halt. Because the force that your foot provides is magnified, amplified many times over, as much as needed, through pressure changes in the car's fluid braking system to provide enough output force necessary to bring the car to a halt. And with that, our lesson comes to an end. See you in class.